Okay, well, welcome to day one of the PLGA nanoparticle synthesis. So before you watch this, you should have watched the lecture that I uploaded to Canvas. You'll see that next to the handout for this module. So handout for the module. Reminder that you can't plagiarize from this document, right? Like this is my text, and so you can't copy and paste from this document and put it into your document, okay? So what we're doing today is basically making oil and vinegar salad dressing, right? We're doing a water and oil emulsion. And that's the exact same thing that happens when you take vinegar and olive oil and you shake it up before you pour it on a salad, right? That's a water and oil immersion, right? Now, what happens to your salad dressing, right? Over time, it settles out into oil and water. And so before you put it on your salad, right, you shake it up and it gets mixed. And that's when you pour it on. But over time it settles back out, right? And so what we're going to do today is basically use a very fancy way of shaking this up such that they never redissolve. They never mix again, okay? We're going to make these emulsions so small that they become colloidally stable. If we're just putting the energy from shaking with your hand, you're going to have your oil and vinegar, right? You're going to have blobs of oil. Inside the water phase or the vinegar phase. And over time, these come back and settle up. But if we can make this smaller and smaller and smaller, we're going to make something that is a stable, colloidally stable nanoparticle. Okay? So that's kind of the big picture. So I talked about in the lecture I uploaded to Canvas of why we would want to put things in a nanoparticle, particularly a drug, right? Stability, delivery, those are probably the main two. The ability to get the target to where the drug to where we want it to. So if we talk a little bit more about what we're going to do today, first you're going to heat your water phase. So this is going to have polyvinyl alcohol that acts like a surfactant in order to facilitate the formation of these particles. The oil phase, which is going to be dichloromethane, is a separate solution. So the first thing we're going to do is make these two separate solutions, okay? Now, I mean, this is kind of an important consideration of where does your drug go, right? Does your drug go here, or does your drug go here? Well, it's kind of a function of your solubility, right? So I've definitely made these before with very, very hydrophobic materials. And in fact, this is frequently often used with very hydrophobic materials. We're using today as a model drug methylene blue, which is relatively hydrophilic, but it's actually amphiphilic. It goes both ways. And so we can put it into dichloromethane as well. Now, what if you had something that was completely hydrophilic? That could not be dissolved in dichloromethane. Would we still be able to make these kinds of particles? The answer is yes, but what we would have to do is what's known as a water-oil-water emulsion, as opposed to what we're doing today, which is just a water and oil emulsion. Okay? So, two different strategies. This is for more hydrophilic, and this is for more hydrophobic. Okay? The other thing, okay, so once we have these, we have our oil, we have our vinegar. Now we've got to shake them up, right? And I talked a little bit in the lecture on Canvas about the effect of free energy and how free energy governs particle size. So I'm not going to talk a lot about it here, except to tell you mechanically the two different methods that we're using. So we're going to make both microparticles and nanoparticles. And based on the equation I showed you on Canvas, more energy is going to give us smaller particles. Okay? So our microparticles is actually going to use just a relatively modified and simplified version of shaking, where we're going to use a stir plate. And our nanoparticles, we're going to use a tissue homogenizer. So this is something that you would, maybe you want to do cell extracts, or maybe you're like taking biopsies or little mouse parts and you want to grind it up and measure the protein in it. This is a device you would use to grind up tissue. There's also a way to make nanoparticles with a probe sonicator. And this puts a ton of energy. So this is increasing order of energy. Right? A stir plate is going to have less energy than this thing. This is going to have less energy than this thing. So let's look at what I'm actually talking about. So the first one is this stir plate. And you guys have seen these before. This is a relatively fancy one where it has 9 individual spots. I don't know if you can see it, but each of these spots has a centered area where we can stir. So this is the tissue homogenizer. And so you can see there's like a guard down here. You might have to zoom in. Actually, let me put some white paper behind it. So you can see it's not spinning right now. But as I turn this on, you'll hear it kick to life and rotate really quickly. Okay, so this is essentially has a little stir bar in there that stirs around. It's okay. Okay? So moving then to even further energy, we have this device. And I'm having issues right now, that's why we're not using it. But this is basically like a glorified electric toothbrush. And so this thing sits and wiggles really, really fast. And it really is the same technology that's in like a Sonicare toothbrush that sits and vibrates junk off of your teeth. But this will just put a ton of energy into whatever liquid you have it in. And you have to actually put it inside of this chamber to protect people's ears. But you can kind of hear it. It's a little whack right now, but you can hear when I turn it on, hopefully, that really high-pitched. So if you use this for long periods of time, you've got to wear earmuffs to protect your earplugs. So these are different ways of basically shaking up your oil and water. Okay, where's my protocol? Here. Okay, so relatively simple. We have our oil. This is getting bad. Water, and we're generally going to have more of the water phase. And for both situations, we're going to take some of this and basically drip it in. We don't want to add it in all at once. And the reason is because that increases the polydispersity and it also increases the size, right? Because that energy that we're dumping into the system is going to be distributed over a larger amount of material. If we drop it in one at a time, the energy that we're putting into it is going to be distributed over a smaller volume. So we're going to slowly drip in our oil phase and then either stir it to make microparticles or tissue homogenizer to make nanoparticles. Okay? But at the end of this, let's just talk about the nanoparticle case. We're going to end up with a batch of particles. Now remember, the oil has our cargo. It has our methylene blue. But I told you that this methylene blue also has some solubility in water. Okay? So if we zoom in here, and this is our nanoparticle, and star equals our methylene blue, there's going to be some diffusion in and out of this cargo, right? Because out here is water, and this is now our oil. It's PLGA in oil. Okay? So there's some equilibrium across these. The other thing that's in here still is this. We still have oil here. We still have dichloromethane. Do you think patients like dichloromethane in their blood veins? No. So after we make this, We're going to gently stir it overnight and allow this dichloromethane to evaporate off, leaving just this PLGA particle. Okay? The next step, like so much in nano, is to centrifuge it. So this would now be on, this would now be technically day 2. So this is part 4 on your handout. So we're going to take our particles, and we're going to spin them down. So all the particles are at the bottom, and the particles have methylene blue inside, right? But I just told you that there's also some methylene blue in solution. So what you're going to do is take this supernatant off and measure you're going to measure the absorbance, right? Or the absorbent, or yeah, optical density. Then, using a standard curve of concentration of MB versus absorbance, you can use this unknown to determine the concentration, right? Basic stuff, okay? So then, once you know the concentration in your supernatant, plus volume of supernatant, you can determine the mass or the moles of methylene blue that is not in your nanoparticles, right? This is a key point. You're determining mass of free cargo. And therefore, also knowing how much cargo or how much methylene blue or how much drug you started with way back at the beginning in step 1 and 2, you can determine what's known as the loading efficiency. Right? Which is mass loaded over mass total. Or maybe it's moles. Moles loaded over moles total. So how would you get this from that data? Well, it's going to be total minus free over total times 100, right? Because this, it's kind of hard to measure. I mean, we're going to do it. It's a little difficult to measure how much is actually loaded, but it's pretty easy to measure how much you have left over, okay? So but you definitely know how much you started with, okay? Total minus free over total equals your loading efficiency, right? So in an ideal case, you would get every single piece of cargo into the particles. But that's probably not what's going to happen, okay? So that is, we just talked about part 5.2 and 5.3, okay? DLS I'm not going to talk about. You guys have spent a lot of time with DLS already. You dilute it, you put it in the instrument, you hit go. So we're going to have that data for you. Okay, the other way that people characterize how well the loading went is the loading capacity. And this is basically what percent of NP is cargo. Okay, so this can be mass of cargo or mass of methylene blue, mass of drug, over mass of nanoparticle. Okay? And so this is going to be in section 5.4, where you take your particles, you wash them, and then you put them back into your solvent, your organic solvent, your dichloromethane. You put them back into the oil. So therefore, they should melt, right? This PLGA is very soluble in the oil phase, and so the polymer is basically just going to melt and release all of its dye. So therefore, when you take particles add in dichloromethane, give it a shake, pretty soon particles are gone, and all you have, these are stars representing free MB. And if you know how much mass, well, so first there's a step here. First step is you just sprinkle in dry particles. You just weigh out dry particles so you know this mass. Then, after they've dissolved and you've released the methylene blue, you can again take this, measure the absorbance, do your standard curve, determine concentration of methylene blue, and then convert to mass of methylene blue. So it will be kind of fun to see how close this matches what you calculated earlier, right? Does total equal mass inside plus free? So the free methylene blue you calculated on section 5.3, right? Here, the mass inside, this is what you're calculating in section 5.4. So ideally, those should add up to what you started with. So that's a good discussion question. Okay? And then the last thing you're going to do in this module is you're just going to kind of simulate a sustained release. So this is now particles in water to simulate blood. Not a very good simulation, but we'll take it. Now, what should happen if we zoom in on this area again? And this is one nanoparticle with dye or drug or cargo on the inside. It's still going to be in equilibrium. Okay? So when we first put this into fresh water, some of this dye is going to come out because at T equals 0, there's no dye in the solvent. It's fresh solvent, right? So we're going to let this sit for a little bit and then come back. So this is T equals 0. At T equals 1, we're going to spin all our particles down, take the supernatant, and just like we talked about before, in terms of using our standard curve, we're going to quantitate concentration of released drug. Then we're going to take this solvent off, right? So right now we're just going to have particles at the bottom of the tube. We're going to add fresh water. Shake it up. And now we're back to where we are here. And so there's going to be again some diffusion. We're going to again spin it down. We're going to again measure the supernatant. We're going to again resuspend it in fresh material. So this is trying to simulate what happens whenever I inject particles into a person or to a mouse, and the mouse is drinking water and peeing water. There's in and out, right? There's an equilibrium. And so this is the notion of fresh liquid going into that living system. Okay? So if we plot this then, these measurements of concentration over time, what we generally see is the highest release is kind of at the beginning, and then it slowly tapers off. And this kind of makes sense, right? That as more and more and more of the cargo diffuses out of the particle, there's less and less that can diffuse with each subsequent time. Okay? Now, a more kind of standard way that people show this is still with time, but they will plot the cumulative amount of drug released. So this will start high, it'll increase pretty quickly, and then it'll kind of plateau. Okay? So this can be kind of your raw data. And this, people will plot this either as like percent of, the best way to plot this is the percent of your total that was loaded. So if you know when you did section 5.4 that, when you did section 5.4 that you loaded, I don't know, 0.8 milligrams per gram of nanoparticle. If this is your loading capacity, and then say you did this experiment in section 5.5 with 1 gram of nanoparticles, you know that the most that can ever be released is 0.8 milligrams. So therefore, the max is like 0.8 milligrams, and you would plot this as a percent of 0.8 milligrams. Okay? So these are the steps that you go through. This one is, there's actually a fair amount of math. It's simple mathematics, but you kind of have to really pay attention to what you're doing, how much volumes you're using. Okay? So go back and watch this again if it's not clear. You can also watch my video on Canvas again, and then we're going to transition, and I'm going to show you some of the lab techniques that you would have used had you been in lab. Okay, you can stop. Okay, so we're going to dive right in. I'm not going to go through as much detail as I did on the silica one because, frankly, at this point, a lot of these are weigh things out, dissolve it, heat it, and I just don't know that it's the best use of your time to watch a video of me weighing things out. So what I am going to tell you is that, so I'm on step 1, day 1. What you missed is that we added 60 mLs of water, we added 1.8 grams of PVA, and we stirred it for an hour or two with stirring and heating to dissolve the PVA. Okay? I didn't do a very good job of explaining in the video PVA. What PVA kind of does is it does help stabilize these microemulsions of particles in the water. And if we didn't have this, no matter how much energy we put into it, it eventually would separate back into oil phase and water phase. And so that's why we can't just have plain old water. We need water with some kind of stabilizer. And that's what this is going to do. So it took us a minute to get it dissolved, but it is dissolved. Okay, so now we're going to put it underneath our homogenizer. And we're putting it in ice because this actually produces a fair amount of energy. And in fact, when I used to make particles with this tip sonicator a lot. And you know, dichloromethane, it's an organic solvent, so it actually evaporates pretty quickly, and you could evaporate it if you don't put it on ice.
So that container is larger.
Oh yeah, good point. So we're just going to switch this over. Try not to get the stir bar. Okay, and then this is going to come down. Okay, now the other thing that you missed is me, or actually Teng-Yu, adding PLGA and methylene blue and dissolving it in dichloromethane. So this is now my dichloromethane solution. So get in here and see how we're going to do this. So zoom down in there and make sure they can really appreciates that this is not touching the bottom, but it's very near the bottom. And then, so first I'm going to turn this on and then slowly add 3.5 mils of the oil phase. So you can see it stirring. And see how I'm putting it in drop by drop? It's at 3.5? No?
I don't remember, but it's in the method. That's enough.
Okay.
Should be enough.
And this is when you turn it off? You turn it off in between?
Yeah.
So we're going to let it turn off for just a minute, stabilize. Okay. So obviously you can appreciate this looks pretty different than the oil phase that we dripped in or the water phase that we started with, right? So the next thing that we would do is we would slowly stir this in a hood in order to allow the extra dichloromethane to evaporate, okay? Leaving particles. Okay, so these are So while that evaporates, we can come over and make our microparticles. Actually, let's pause right there. So this is now part 3.2, and we're going to make the microparticles. And so here we're just simply using a stir situation, a stir plate. So you can appreciate I've got this scintillation vial, and there's a stir bar in the bottom, and if you come in and zoom, you can see it stirring. And I'm going to add 500 microliters of my oil phase. Again, doing this dropwise. And then we would allow this to react for an hour or so. And this is nice because here our DCM will largely evaporate during this process. Okay. Okay, so we've now allowed the solvent to evaporate off of the nanoparticles. And so we're going to proceed now with part 4A. I'm just going to pour it off. And so you can see it's very cloudy. And I have a batch that I actually centrifuged previously. And so you can see our particles that we've collected, and you can also see the supernatant. And so, as you can tell, I mean, a lot of the material is actually not encapsulated, right? This is totally a function of the solubility. For example, I was making these particles, PLGA particles, previously with a very hydrophobic material, and almost all of it was encapsulated inside of the nanoparticles. But here we're getting a relatively small fraction. Okay? So the next thing you would have done if you were here is we would have redissolved this and do DLS. The other thing that we would have done with some of those dissolved particles is we would have done lyophilization. And so that's section 4F. So let's pause here and go upstairs and I can show you the lyophilizer. Okay, so this is a lyophilizer, which is also known as a freeze dryer. So if you've ever gone camping and you've had freeze-dried fruit, or what else is freeze-dried? That's probably the most common, like you see it in food. This is something that does that. So if you look at what we're looking at right here, you can see the pressure that is inside of here. So 0.27 millibar. So a pretty low pressure. I don't know what that converts to in atmospheres, but I know it's a really low vacuum because we have a low high pressure vacuum back here that is pulling pressure off of the system. Okay? So this negative pressure is going into this chamber. And so if you look down into this chamber too, you can see that it has all of these different ports coming into it. Okay? Now down inside of there is an area that's cold. And so what's happening is as solvent comes off, it goes into this center chamber and then is condensed and forms ice. Okay? So what you would have done if you were here is you would have first redissolved your particles into a solvent after washing them a couple times, and you would have froze it, okay? Then, while it's still frozen, you would put it inside of one of these little chambers and turned on the vacuum in order to pull negative pressure. So you're basically putting ice in a vacuum. And what happens is the solvent sublimates, and it's kind of magic because what you're left with is this really fine, beautiful powder. And this is what this is stable, you can store this at room temperature. It's basically a way of purifying, stabilizing a number of different materials. So this obviously doesn't have any methylene blue in it, but this is what you would get as this particle was refined with this process. So this is what a lyophilizer looks like. Okay, so also coming back to our microparticles, one thing you can appreciate is indeed because of their larger size, see how they've kind of settled here? Notice how clear the supernatant is, and I'm going to stir it a little bit, and now you can see that the particles have resuspended, but because they're not nanoparticles, because they are microparticles, they are not colloidally stable, and so they tend to settle. So you can appreciate if I swirl it again, there's more cloudy, and then as it slowly settles over time. So these would be purified very similarly, centrifuge, wash, centrifuge, wash. So now as we move on to, point 5.2 to 5.5, I'm not going to walk you through this because basically all it is pipetting. And again, I don't think having you watch me pipette is going to be a particularly enriching experience for you. But what I do hope that you learned is some of the equipment that would have been accessible, including the lyophilizer upstairs. I also hope you learned some of the principles underlying the mathematics. So really go back and make sure that you understand what we're doing in loading capacity, loading efficiency, and on our drug release curve, okay? Of course, as always, feel free to reach out with any questions. Email is way better for me than a message through Canvas. It's just jjokerst@ucsd. So with that, this is going to be due, it's on the syllabus. Today is the 15th. I'm going to give you this on the 16th, and it's due a week from then. So best of luck, and we'll see you on Module 5.